Ever wondered how everything around us came into existence? What was the trigger that led to the birth of our universe? Let's embark on a cosmic journey back to the very beginning, to the Big Bang. The Big Bang Theory, it's not just a popular TV show, it's the prevailing cosmological model that explains the origin of our universe. It paints a picture of a universe that exploded into existence from an extremely hot, dense point roughly 13.8 billion years ago, a moment we often refer to as the singularity. Imagine, if you will, all the matter and energy in the universe compressed into an infinitely small, infinitely hot, and infinitely dense point. This point, this singularity, is thought to have contained everything that would eventually become the universe we know today. Quite a thought, isn't it? But what triggered this colossal event? Well, that's a question that even the most brilliant minds are still grappling with. The singularity didn't exist within space. Rather, space, as we understand it, began within this singularity. As it expanded, it created not only matter and energy, but space and time as well. As the universe expanded, it also began to cool down. Within the first few minutes, subatomic particles like protons, neutrons, and electrons formed. This marked the beginning of the universe as we understand it today. From this intense heat and subsequent cooling, the stage was set for the birth of atoms, the building blocks of matter. While the concept of the Big Bang might seem abstract and even a little intimidating, it's a theory that has stood the test of time, continually being confirmed by observational evidence. Despite its complexities, it remains the best explanation we have for how our universe began. So, the universe as we know it began from a tiny, dense singularity, expanding rapidly into the vast cosmos we are part of today. An incredible journey, don't you think? Now, imagine the universe expanding and cooling down after the Big Bang. What happened next? Let's dive in and explore the aftermath of this monumental event. As the universe rapidly expanded from its initial high-density, high-temperature state, it started to cool. This cooling wasn't like turning down the thermostat on a hot summer day. Oh no, it was an epic cosmic cool down that lasted millions of years, and it changed everything. During this period, the universe went through a phase known as nucleosynthesis. This is a fancy term that essentially means the creation of atomic nuclei. In the extreme heat and density of the early universe, the basic building blocks of matter, subatomic particles like protons and neutrons, began to form. As the universe continued to cool, these particles began to combine to form the nuclei of simple elements, hydrogen and helium. These elements, in their ionized state, made up a hot, dense soup that filled the universe. Meanwhile, another critical player was also coming into existence, the electron. Electrons are tiny compared to protons and neutrons, but they play a vital role in the structure of atoms and the nature of chemical reactions. Now, these particles didn't just randomly appear. Their formation was a result of the universe's conditions at that time. The universe was essentially a giant expanding particle accelerator, creating and transforming particles in ways that we're still trying to fully understand. By the time the universe was 3 minutes old, about 98% of all the matter that exists today had been created. But it wasn't yet in the form we recognize. It was a hot, dense, ionized soup of particles, a state known as a plasma. And thus, the stage was set for the universe to evolve with the creation of these subatomic particles. These particles, the simplest building blocks of matter, would eventually come together to create everything we see in the universe today. The stars in the night sky, the earth beneath our feet, and even us. We all started with these tiny particles in the aftermath of the Big Bang. A scene script. Evidence is crucial in science. So, what's the evidence that supports the Big Bang Theory? In the quest to understand our universe's origin, astronomers stumbled upon a game-changing discovery in the 1960s. They detected a faint, almost imperceptible glow filling every corner of the sky. This glow, known as the cosmic microwave background radiation, or CMBR, is like the afterglow of a grand cosmic firework, the Big Bang. The CMBR is a relic from a time when the universe was just a baby, a mere 380,000 years old. Back then, the cosmos was a hot, dense soup of charged particles and light. As the universe expanded, it cooled down, and particles began to combine to form neutral atoms. This process, known as recombination, made the universe transparent to light for the first time. The light released during this epoch traveled across the universe, reaching us over 13 billion years later as the CMBR. The CMBR is incredibly uniform, with tiny temperature fluctuations of only about 1 part in 100,000. These minute variations are critical. They provide a snapshot of the universe at a very early stage, offering clues about the initial conditions of the Big Bang. Moreover, these fluctuations led to the formation of large-scale structures like galaxies and clusters of galaxies that we see today. In a sense, the CMBR serves as a baby picture of the universe. It's an image of the cosmos when it was very young, long before stars and galaxies formed. By studying this cosmic relic, scientists can learn about the universe's birth, its composition, and its ultimate fate. Importantly, the discovery of the CMBR gave the Big Bang Theory a significant boost. It provided tangible evidence that the universe did indeed start in a hot, dense state and has been expanding ever since. The CMBR is a testament to the power of scientific prediction and a cornerstone of our current understanding of the cosmos. The discovery of cosmic microwave background radiation was a landmark moment, solidifying the Big Bang Theory's position in our understanding of the universe. From the primordial soup of the early universe, how did we get to the diverse array of elements we see today? To answer this question, let's take a step back to the aftermath of the Big Bang. As the universe expanded and cooled, the first atoms began to take shape. These were primarily hydrogen and helium, the simplest and lightest elements in the periodic table. Their formation marked a significant turning point in the evolution of the universe. Now you might wonder, how did we get from hydrogen and helium to the rest of the elements on the periodic table? That's where stars come into play. Stars are like cosmic factories, forging heavier elements through a process known as nuclear fusion. In the extreme heat and pressure of a star's core, hydrogen atoms combine to form helium. This process releases a tremendous amount of energy, which we see as the light and heat radiating from stars. But the story doesn't end with helium. As stars age and exhaust their hydrogen fuel, they begin fusing helium atoms together, creating even heavier elements like carbon, oxygen, and so on. This stellar alchemy continues until iron, the most stable element, is formed. In the most massive stars, the formation of iron triggers a spectacular finale, a supernova explosion. These cosmic fireworks don't just light up the universe, they also spew out a cornucopia of heavier elements, including gold, uranium, and everything in between. These elements, scattered across the cosmos, eventually coalesce to form new stars, planets, and even life itself. Fast forward to the present day, and we find ourselves in a universe teeming with a dazzling array of celestial objects. Galaxies filled with countless stars, planets, asteroids, comets, and more. Each and every one of these objects, including you and me, owe their existence to the cosmic processes set in motion by the Big Bang. Over billions of years, the universe has evolved from a hot, dense singularity to the vast, diverse cosmos we see today. Despite our understanding of the Big Bang and the universe's evolution, mysteries remain. Have you heard of dark matter and dark energy? These elusive substances are not directly observable with any of our current technology, yet they make up about 95% of the universe. Dark matter, despite being invisible, exerts a gravitational pull on galaxies, holding them together. This unseen force was first proposed when scientists noticed galaxies were spinning faster than they should be according to visible matter alone. Then there's dark energy, even more mysterious. It's believed to be the driving force behind the universe's accelerating expansion. In the late 90s, astronomers observing distant supernovae found them to be moving away from us faster than expected. This observation led to the proposal of dark energy, a sort of anti-gravity force pervading all of space. Scientists around the globe are tirelessly working to crack these cosmic conundrums. They're using sophisticated technology, like the Hubble Space Telescope and the Large Hadron Collider, in their quest to understand these dark entities better. It's a thrilling time to be alive as we stand on the precipice of major breakthroughs in our understanding of the universe. Dark matter and dark energy, the universe's mysterious components, continue to push the boundaries of our understanding.